Welcome back, everyone. Ready for another deep dive? Today, we're going to try to wrap our heads around something pretty incredible, Einstein's theory of general relativity.
It's a big one for sure.
Yeah, no kidding. I mean, we're talking about the theory that completely revolutionized our understanding of gravity. It's kind of a big deal.
Absolutely. It's one of those pillars of modern physics that touches on so many aspects of the universe, from the smallest particles to the largest structures.
Right. And it all starts with this really wild idea that gravity isn't just a force, it's actually the curvature of space and time itself.
I know it sounds crazy, right?
Yeah.
Like, how can something we experience every day be so different from what we thought it was?
Yeah, exactly. Like I jump up, I come back down.
Right.
That's gravity simple, right? But Einstein came along and said, hold on, there's a whole lot more going on than meets the eye.
He did. And to really understand general relativity, we kind of have to rethink our whole concept of what gravity is all about.
Okay, so let's do it. Let's break it down. Where do we even begin?
Well, a good place to start is with Newton's idea of gravity.
Right.
You know, the whole apple falling from the tree thing.
Right, classic story. So Newton figured out that there's this force of attraction between any two objects with mass.
Exactly. And that force depends on how massive those objects are and how far apart they are.
Yeah.
So the more massive the object, the stronger its gravitational pull.
Makes sense.
Yeah.
And the closer you are to something, the stronger its gravity feels.
Right. So for centuries, Newton's law of universal gravitation was the gold standard for explaining how gravity worked. It could predict the motion of planets, the tides, all sorts of things.
It's like gravity 101, right? But then Einstein came along and said, actually.
Pretty much. He realized that Newton's theory, while incredibly useful, had some limitations. It couldn't quite explain everything.
Okay, so what were those limitations? Where did Newton's apple cart start to wobble?
Well, one of the biggies was the orbit of Mercury. See, astronomers have been tracking its movement very precisely, and they noticed something strange.
Strange how?
Well, Mercury's orbit wasn't behaving exactly as Newton's theory predicted. It was slightly off.
Awfully. How much are we talking about here? A little nudge or a major cosmic detour?
It was subtle, but definitely measurable. And it bugged the heck out of scientists because Newton's theory had been so successful in explaining other planetary motions.
So they knew something else had to be going on, some other factor that Newton's theory wasn't accounting for.
Exactly. And that's where Einstein's genius comes in. He proposed a radically different way of thinking about gravity.
All right, Einstein lay it on us then. What was his big idea?
Instead of viewing gravity as a force acting across space, Einstein imagined it as a property of space itself, or more accurately, a property of space-time.
Space-time. Okay, we're already diving into the deep end here.
I know it's a lot to take in, but stick with me. Think of space-time like a giant flexible sheet, almost like a trampoline.
I'm picturing it. Go on.
Now imagine you place a bowling ball in the middle of that sheet. What happens?
Well, the bowling ball would create a dip in the sheet, right? It would warp the fabric around it.
Exactly. And this is essentially what Einstein said massive objects do to space-time. They create these cosmic curves and everything else, planets, light, even time itself is affected by this warping.
Hold on, wait a minute. We're already talking about bending time. This is where my brain starts to feel a bit fuzzy.
I understand. It's a lot to wrap your head around. But think of it this way. Imagine an ant crawling on a flat sheet of paper. To that ant, its world is two-dimensional. It doesn't experience up or down.
We, on the other hand, can see the entire sheet, including the third dimension that the ant is unaware of.
Precisely. We experience time linearly as this constant flow, but Einstein proposed that it's not separate from space. They're woven together into this four-dimensional fabric he called space-time.
Okay, so space-time is like this invisible stage where the cosmic dance takes place. And the more massive the objects, the more they warp the stage itself.
Precisely. And here's the really fascinating part. It's not just the mass of an object that influences space-time. It's energy, too.
You're saying that even something like light, which doesn't have mass in the traditional sense, can still affect the curvature of space-time.
Exactly. And this brings us to Einstein's famous equation, E v c c.
Okay, everyone's heard of ECC, but honestly, what does it really mean? EVC, it's like the rock star equation of physics. But what's the deeper meaning behind it?
At its core, EPCC reveals this incredible connection between energy and mass. It tells us they're actually interchangeable, two sides of the same cosmic coin.
So energy can become mass and mass can become energy? Is that what powers the sun?
Exactly. The sun is a giant nuclear fusion reactor converting mass into energy constantly. And that energy radiating outward isn't just light and heat, it's also subtly influencing the curvature of space-time around it.
Wait, so you're telling me that the sunlight hitting my face right now is actually carrying a tiny bit of gravity?
In a sense, yes. It's a tiny effect, incredibly small, but it's there. And it highlights this profound idea that mass and energy work together to shape the universe we experience.
That's incredible. But if this mass-energy equivalence is so fundamental to general relativity, why isn't EMC4 explicitly written out in those famously complex Einstein field
Great
equations?
question. Well, Enid sheet doesn't appear directly in the field equations. It's woven into their very fabric. Think of the field equations as a set of rules describing how everything in the universe interacts with the curvature of spacetime.
Everything, including that pesky energy-mass combo we've been talking about.
Precisely. The field equations take into account both mass and energy when describing how spacetime bends and curves. They're like a cosmic recipe with ENC4 as a key ingredient.
So we've got this mind-bending idea of space-time as this flexible fabric that gets warped by mass and energy. This is already blowing my mind. But how does this actually play out in the universe? What are the observable effects?
One of the most fascinating predictions of general relativity is that gravity can actually bend the path of light itself.
Wait, really? Gravity can bend light. You're going to have to explain this one.
Imagine a beam of light traveling through space. Now picture a massive object like a cluster of galaxies sitting in its path. According to general relativity, that massive object will warp the space-time around it, causing the light to bend as it passes by.
So it's like light taking a detour because gravity is literally changing the road it's traveling on.
Exactly. And this phenomenon isn't just theoretical, we've actually observed it. It's called gravitational lensing.
Gravitational lensing. Tell me more.
Imagine looking at a distant galaxy, billions of light years away. Now imagine there's a massive object, like another galaxy cluster, between us and that distant galaxy. The gravity of that closer cluster can act like a lens, bending and distorting the light from the more distant one.
So instead of seeing the distant galaxy directly, we'd see its light warped and magnified by the gravity of the closer cluster.
Exactly. And that's exactly what astronomers have observed. These stunning arcs, rings, and multiple images of distant galaxies, all thanks to the warping power of gravity.
Wow. So we're not just talking about some abstract theory here. General relativity has given us this incredible tool to observe and study the universe in a whole new way.
And it's not just about looking at pretty pictures. Gravitational lensing allows astronomers to study objects that would otherwise be too faint to see. It's like having a giant magnifying glass in space.
That's amazing. So we've got warped light courtesy of curved spacetime. What other mind-blowing predictions came out of general relativity?
Well, there's the existence of black holes, regions of space-time, where gravity is so intense that nothing, not even light, can escape. And then there are gravitational waves, ripples in the fabric of space-time itself, caused by some of the most violent events in the cosmos.
Gravitational waves. Those were actually detected recently, right? That was huge news.
It was a groundbreaking discovery. In 2015, scientists at the Laser Interferometer Gravitational Wave Observatory, or LIGO for short, made the first direct detection of gravitational waves, confirming Einstein's prediction from a century earlier.
So after decades of searching, we finally had proof that these ripples in space-time were real. That must have sent shockwaves through the scientific community.
It was a watershed moment. It provided concrete evidence for a key aspect of general relativity and opened up a whole new avenue for studying the universe.
Okay, so we've covered a lot of ground here, from the mind-bending implications of EMC to the awe-inspiring phenomena of gravitational lensing and gravitational waves. But let's bring things back down to Earth for a moment. How does general relativity impact our everyday lives?
You might be surprised to learn that general relativity plays a crucial role in a technology many of us use everyday: GPS.
Wait, really? My phone relies on Einstein's theories to tell me where I am. Now that's what I call a practical application.
It's true. GPS satellites orbiting Earth have to account for the effects of general relativity, specifically a phenomenon known as time dilation.
Time dilation. Okay, you're going to have to break this one down for me.
So we typically think of time as constant ticking away at the same rate everywhere. But according to general relativity, gravity actually affects the flow of time.
You're saying time can move faster or slower, depending on where you are?
Exactly. The stronger the gravitational field, the slower time passes relative to a weaker gravitational field.
So because GPS satellites are further from Earth's gravity than we are, time actually moves slightly faster for them.
That's right. It's a tiny difference, but it's enough to throw off GPS calculations by several miles per day if we didn't account for it.
So my phone is constantly making tiny adjustments based on Einstein's theories just so I can find the nearest coffee shop. That's both amazing and slightly terrifying.
It's a testament to the power of general relativity that we can use it to navigate our daily lives, even if we don't realize it's happening behind the scenes.
This has been an incredible journey so far, from the theoretical foundations of general relativity to its mind-blowing implications for the universe and even our everyday lives. But before we wrap up, I have one more question for you. If gravity can actually influence time, does that mean time travel might be possible? Time travel. It's the ultimate science fiction fantasy, but is there any real science behind it?
Well, time travel is a topic for another deep dive entirely. But you're right to connect it to general relativity because Einstein's theory really threw our old ideas about time out the window.
So you're saying there's a chance. Don't leave me hanging.
Let's just say that general relativity opens up some seriously intriguing possibilities. While building a time machine might still be in the realm of science fiction, the idea that time isn't absolute, that it can be stretched and squeezed by gravity, is no longer up for debate.
So hypothetically, if I were to hang out near a black hole where gravity is super strong, time would pass differently for me than for someone back on Earth.
Precisely. Think about it this way. Time flows more slowly in stronger gravitational fields. So if you were close to a black hole and your friend was back on Earth, you'd age at different rates. Your friend would experience time much faster than you.
So I'd come back from my black hole vacation younger than my friend? That's one way to win at aging. But seriously, that's incredible though. A bit tough to wrap my head around.
It challenges our everyday intuition about time, for sure. But remember that intuition developed in a world where gravity is relatively constant.
Right here on Earth, where what goes up must come down and time marches on regardless.
Exactly. But general relativity reveals that those rules aren't universal. They're just local experiences shaped by our particular position in the cosmos.
Okay, so time travel aside, are there any other mind-blowing implications of general relativity that we haven't touched on yet?
One of the most profound is its impact on our understanding of the universe as a whole. General relativity provides the foundation for cosmology, the study of the origin, evolution, and large-scale structure of the universe.
So it's not just about planets and stars, but about the big picture, how the entire universe came to be.
Exactly. General relativity allows us to describe the expansion of the universe, the formation of galaxies, and the behavior of the universe on the grandest scales.
It's like going from studying individual brushstrokes to appreciating the entire masterpiece.
That's a great analogy. And just like a masterpiece, the universe as revealed by general relativity is full of awe-inspiring beauty and mind-boggling complexity.
Well, I have to say, this deep dive has been quite a journey. We've gone from the familiar feeling of gravity here on Earth to the mind-bending reality of curved space-time gravitational lensing and even the possibility of time travel.
It's a testament to the power of Einstein's theory, that it can explain such a wide range of phenomena, from the motion of planets to the fate of the universe itself.
It's incredible to think that one person's ideas could revolutionize our understanding of the cosmos so profoundly.
And it's a reminder that the universe is full of mysteries waiting to be unlocked. Who knows what other groundbreaking discoveries await us in the future?
Well said. For anyone listening feeling a bit overwhelmed right now, trust me, you're not alone. Wrapping your head around general relativity takes time and effort. But the payoff is a whole new perspective on the universe and our place in it.
It's a journey worth taking, for sure.
Absolutely. So keep asking questions, keep exploring, and keep your mind open to the wonders of the cosmos because, as Einstein himself once said, the most beautiful thing we can experience is the mysterious. It is the source of all true art and science. And on that note, we'll wrap up this deep dive into Einstein's universe. Until next time, keep looking up and never stop questioning.